Hello, Internet. Today, I wanted to take a look at steering algorithms. I think that's the sort of class of problems we're going to be working on. And it is sort of a class of problems. It talks about a whole bunch of different things about moving an object and steering it towards some specific objective. I want to specifically look at how to make something dodge some other thing. So if there is an obstacle in its way, it is going to automatically steer out of the way of whatever that obstacle is and take the best of its ability to get out of its way. So maybe it's a spaceship or something. We're going to be working in 2D because that's easier, but I don't actually think that's going to change anything. I've never done this, so who knows how it's going to go, but hopefully it goes well. The general idea is we are going to have some sort of object, some sort of ship, and that ship is going to project a series of rays in front of it. And this is sort of going to be its field of view, its cone, I guess. And if anything enters that field, it's going to steer away from it. So if something's directly in front, it will take the nearest available path of all of those rays. If there isn't one, it will do something that we haven't figured out yet. Hopefully that doesn't happen too often. But if there's one coming in from the side, it will steer in the opposite direction. So each ray that it receives an input is going to apply a negative force in that direction. So if there's something directly to the left, it is going to apply force in the right direction. And that is going to cause the ship to turn in that direction. And we can add as many rays as we want and make them as forceful as we want, but that's pretty much how it's going to be. And if there isn't anything impacting that ray, it's just going to thrust in that direction. So typically it should just go straight forward. But then as things become occluded, as things get in the way, it should automatically steer around them. I say we're doing in 2D because if we did it in 3D, we'd have to do a cone. And that's just more work. So we're going to skip that and just do 2D because then we can just use a single axis instead of trying to do multiple and do some like spin and it just make it more complicated. So we're not going to bother with that. The same ideas that we're covering should work. It's just more complicated and it's just going to take more time for not too much more usefulness. So there's not too much extra stuff that would be added there. So we're going to create a avoiding flyer script. That's it's a weird name. And so we're just going to start writing this and see how it goes. I kind of described what I'm thinking should work. I don't actually know if that's how we're going to do this, but we're going to have a target velocity, and then that's going to be divided by the number of rays. So we will say public float target velocity equals, say, 10. We can change that later, and then public int number of rays, and that will be 20. Let's make this so if we do an even number, there is a problem with that because we're starting on one side and moving to the other. Either our cone is going to be offset and our ship will kind of constantly move in that offset direction, or we won't have anything looking directly ahead of us. And so we probably want that, so that's what we're going to do. We're going to set this to 17. Or Visual Studio's going to think about setting it. There we go. Okay, it's working. It's just working very slowly. And then public float. We want like an angle here. So I'm going to set this to. How do I want to do this? Let's do 90. And this will be doubled. Well, it sounds weird, but this way we can go 90 degrees from forward in both directions. So as you increase it, it does double because it's going from the center. I don't know if that's the best way to reason about that, but that's what I'm doing. You can obviously change that and just do some division if you want to get back to this and get the same numbers. This is just an input, so you can make that whatever you want. So rays. We're going to be using physics.raycast to do all of this. And so we just need to generate a whole bunch of these. But before we do that, we actually need two things. We're going to need a direction for the ray, and we're going to need a point. We have the point, but we don't have a direction because all of these need to be in that arc. So the first thing we're going to do is actually not physics.raycast, I don't think. Instead, we're going to do void on draw gizmos. This will give us a nice visual way to kind of visualize how these rays are going to appear. And so what we want to do is do for each, int I equals 0, I less than number of rays, and increment I. Let me make this a little bit bigger for you, just so it's hopefully easier. Why doesn't that shortcut doesn't work in Visual Studio? Hold on, I can fix this. I'm gonna make the screen bigger, and I will be right back. So I will be right back. Okay. There. Hopefully that's a little bit clearer. Yeah, it just, with scaling and everything, that the previous text would have been hard to read. So this is hopefully a little bit better. We have our for loop that's just going to loop over everything. Why is this so slow? Okay, it's thinking a lot apparently, and that's probably not a good sign. But we're not doing much, so who knows? It's Visual Studio things. So we need to start from the left side. Let's just start on the left and go across like that. I don't know how we're going to do that though. So let's see. We need an angle. So let's just take vector3 dot forward, and we need to rotate this to the left. The easiest way to do that is probably to construct a quaternion and just, is that the best way? I think we can do vector3 dot rotate towards target. That should work, but I don't know if I want to do that. So the problem with rotate towards is it's going to rotate this thing in a specific direction. I think I've been thinking that there's another way to do this, and there is with quaternions. But I didn't really want to use them. So we are going to create an angle. There's a few other, so there's a lot of ways to do this. I could not do any of this at all. This is not strictly required, but it's something that we probably are going to want. So equals this transform dot rotation. Let's just grab our current rotation. That makes much more sense. This is the part that I was a little bit confused about in my head. I wasn't super sure how we were going to do this. Going back to this, it's relatively easy in 2D to make this work because we can just use sine and cosine to get that. It's more complicated once we get beyond that because those formulas don't really do the same thing anymore. And if we want, for every other part of it, it doesn't really work. So trying to use something that is more uniform, I guess, is more difficult. Otherwise, we could, just sine and cosine it and get normal stuff. But what I actually want to do is take that rotation and shift it in one way or the other. So rotation dot, or actually, oh, this is hard. This is hard because I don't know if there's a good way to do this, actually. This may have been a mistake. Because, so we want to rotate this around an axis. Quaternion dot rotate, axis? Angle axis. That's better. Okay. What am I doing? Rotation, that's our current direction forward. All right, back on track. Totally got lost there. Got sidetracked by a whole bunch of random things, but angle axis is actually what we're going to want. And this is going to give us a rotation around an axis. The nice thing about this is we can provide any axis we want and any value we want. So we are going to provide number of rays times, or angle divided by the number of rays. I divided by the number of rays times the angle. And so this is what this is going to end up looking like. And then we need an axis to rotate this around. So this is going to be this transform dot up. So just the up vector. We could do this also in world space if we wanted to. That will lock us to a specific plane. This way it's a plane that can shift, which again, may not be the best of choices. These are both integers though, so we're actually always going to get 0 here. Because the result will get truncated because should always be less than the number of rays, so it'll always reduce to 0. So we need one of those to be a float, and that will give us some fraction of an angle. And we need to save that. Var rotation mod. Sure. And so we can actually add these two quaternions together. This isn't quite what we want, but it's close. So we have our rotation, our base rotation, and then we have some sort of modifier to it that we're going to apply. And so we should just be able to apply that for each of these and get a new gizmo dot draw ray. This transform position. And then our rotation times the rotation mod. If fire. So that is a quaternion, but that is not a vector. So we actually need to turn this into a direction. How do I do that? Let's see, rotation dot forward. That's not gonna work. That will give us the angles, the normalized. Another thing that I'm not entirely sure how to do, actually. So we're going to figure that out. Projection. No. That is not what we want. What the heck? I swear I knew, or I thought I knew what I was doing when I started this, but clearly I didn't. New vector 3. Can I just do that? I don't think I can, because that's going to be the wrong thing. So that's going to be a quaternion is technically like a 4-dimensional vector. That's sort of how it ends up working. In order to avoid some of the complexities of 3-dimensional rotation in 3D space, they add a 4th dimension and it does magic. I don't really know how that works, but there's magic there. And we need to figure out how to take that magic quaternion and translate it into a unit vector in the direction we want. And so we're going to modify or multiply both of these rotations to get us a direction. And then along that direction, we need to create a vector. And I need to figure out how to do that because I don't know. So I'm going to actually look this up, how to turn a quaternion into that. And then we will figure it out. And do that. Probably should have done this first, but I thought I knew how to do this, and I've forgotten. So anyway, I'll be right back. I think this works. I think I figured out how to do this, and you just multiply. We were multiplying the rotation times the rotation modifier, which is in quaternions that adds them together. And then we were multiplying. The new thing is to multiply it by a forward vector, so z equals 1. That should translate it into a vector for us, and we should be able to work with it. I think I've done this in the past, but I don't remember it. So this may or may not work. I haven't tested it, so we'll find out. But this seems like it makes sense to me, so we're gonna try it. The alternative is to get the Euler angles out of it and do some trig to figure out how to do it all. I don't want to do that, so we're gonna try to avoid that if we can. But yeah, there we go. That should draw 17 rays for us. So what we want is just a cube that gets added, and then avoiding flyer. If we attach that, there are 17. Is that 17? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, close enough. So there should be 17-ish lines there, and they're a 90-degree segment. So we need to spread those out a little bit more by going here and changing this formula a little bit. So right now it's I divided by number of rays. We actually want something else. So I divided by the number of rays times angle times 2 minus the angle. In hindsight, we probably could have just made that 180, but it doesn't matter. This is fine. So what this is doing is doubling the range because these are all multiplications. That's sort of the range of our formula. And then this subtraction is sort of the starting point. We're now starting at negative 90 and moving all the way to 180 or double 90. And so that should help there. We might be off by 1 because so we're off by 1 here, and that's sort of expected. The reason that's happening is because this is going from I equals 0 to I is 1 less than the number of rays. So we have 17 here, so it's going to be, the maximum we're going to get is 16 over 17, which isn't 1, which means that our first value at 0 is going to be at negative 90, and then the other one is not going to reach 180. And so we can actually sort of solve this by making this a less than or equal to, but that actually breaks everything. That means instead of drawing 17 rays, we're actually drawing 18. And we don't want that. So what we could do, and what we might actually just do, is just subtract 1 from the number of rays. This should fix it because it reduces the range to what the actual range is. Alternatively, we could just take this value here and add half. But that means that it won't go from the negative 90 point. It'll go from something slightly less than that. So this should get us something more accurate, and we'll actually get them correct. So you can see the line goes straight through instead of like taking a weird turn. So there are our detectors, I guess. So there we go. So now we just need to take that logic and apply it to actual movement. So what we're going to do is public float ray range equals 2, and just do that. And for this, I think we're just going to have it. We're not going to add a velocity. We could, but it's the same kind of concept. Velocity just means that this may require more tweaking and may require more work. It's the same idea. Well, what we're doing is we're detecting if there's something there and then applying some force or taking some action. What that action is doesn't really matter. In this case, it's going to be a static force. So we are going to have some sort of value of movement. So we're just going to store a vector and store the movement of that vector and then apply that to whatever it is. So here is all of this. We don't need the Gizmos bit, but we're going to copy all of this. So let's just grab it. Put it there and drop the Gizmos bit. And so now we have all of these directional things. So we have a bunch of directional vectors. So let's just physics.raycast along a new ray. And we'll take the, do we even need the hit info? I don't think we do. We could take it, I guess. So let's just grab it because why not? And then the max distance is our ray range, and that will be our raycast. So we are going to do if physics.raycast does this. If we actually collide with something, we'll do that. Otherwise, we'll do this other bit. So there is our conditional stuff. And now we just need this ray and the hit info. So we have raycast hit, which is our hit info. And so this is an output value or output variable, which means that it is just a reference that we're storing. And then this function is effectively returning that. So it is going to provide a second return value effectively that is stored in hit info. And so we can use that later to get more information about what we hit. And this, we're not going to be looking at that too much. But if you want to detect like only detected enemies or something like that, or only dodge bullets, for example, this is how you might approach that. We're going to do this though and create a ray. So new ray of an origin, which is this .transform.position and a direction. So this should already be normalized because it's a rotation of this forward vector. So I think this should be fine. And yeah, there's our ray, there's our hit info. That should determine if we hit anything. What we're going to do though is store a var flyer movement. Let's do delta position equals vector3.0. So there's no delta position or no movement initially, but if we collide with something, we want to do delta position plus equals 1.0f divided by our number of rays times the target velocity. We're just going to wrap this so it's more clear about how the order of operations is intended to go. It shouldn't be a problem, but this just hopefully makes it a little clearer. And it doesn't like that. Cannot be applied to type vector3 and float. Oh, so this is the scalar. Sorry, I'm missing a part. So this is the scalar that we're getting. What we actually want to do is also multiply that by our direction. So the direction is the current direction this thing is facing. So in this case, we have all of that, but we hit something. So we're actually going to subtract this function. And then up down here, let's add it. So if we don't collide with anything, we're going to move in the direction that we didn't hit anything in. If we do hit something, we're going to move away from it. If you're doing force things, this would be like subtract force or subtract velocity or whatever. But we're just modifying the position. So at the end of this, we can just do this dot transform dot position plus equals delta position times the time delta. And that should cause it to move however it makes sense. This may seem a little bit weird because we're actually like doing instant movement, so there is no velocity. So it might react a little bit faster than you might expect. But hopefully, yeah. So you can see now, right now, it's moving straight along that forward path. But if we put something in its way, let's just grab, we could do spheres, we could do cubes. Let's do spheres because why not? Also, that is not on the right plane. There we go. So let's find wherever this is supposed to be. There we go. And we'll just put this here. I'm kind of curious what happens if we put it directly in front. It might just stop it because it will try to move, or it'll just collide into it because we don't have anything that will turn it in one way or the other if there's something in the way. That's something that we could do with a number of different solutions. I don't really know what the best one is, so we're just going to make it up. But there's a bunch of things for it to run into, and we'll see what happens. Hopefully, okay. In this case, it's just colliding with a bunch of things, so it's bouncing back and forth. Because it doesn't steer out of the way, it's just going to stick. So we can actually solve this by just moving that, and you can see once we move it just slightly out of the way, it weaves around all those obstacles. And that was actually pretty cool. So let's copy these, move that. So one of the things is I don't actually know where this is going to fly to. So kind of making up this path as I go, but it should be able to figure out its way out the other end somehow. But this is super basic, I'm hoping, for an introduction to this. You can kind of see it's dodging out of the way of things. And that's sort of the simplest way we could approach this. Again, it gets more complicated if we start doing more dimensions or more complex interactions. But the general idea is the same. And you just can make this really basic formula that we're doing of one line a little bit more complicated and have it do whatever makes sense. Maybe you want to apply a rotation instead of actually just changing the velocity. Things like that are possibilities. But I think this sort of covers the basics of it. It kind of goes through the basics of how to do this and just a whole bunch of raycasts. That works. So yeah, this is how to get started with this type of steering algorithm. So if there's other questions you have, or you have other ideas about how we could use this, let me know. if there's other steering or AI or pathfinding type things you want me to take a look at, let me know that as well. I'm kind of curious, and it's one of those areas that can get deceptively complicated. So hopefully this is interesting and you can use it in your projects. But until next time, see you, Internet.